Hello, good morning, good afternoon, whenever you're watching this. Today we're going to go into Hooke's Law. We just wrapped up with friction, and you guys used formulas that looked kind of like this. You were solving for the magnitude of force or the coefficient of friction, whether it's kinetic or static. Just a reminder that static friction is the force required to overcome friction of an object that's sitting still, and then kinetic friction is the forces required to keep an object moving once you've already overcome the static friction. So static friction should always be a little bit higher than kinetic friction, sometimes double, sometimes not quite as big of a difference depending on that coefficient. Coefficients do not have a unit, okay, and most of the time these fall between 0 and 1. Sometimes they're just slightly over 1. So that's kind of the range of things you're looking at there. So like I said, we're going to get started with Hooke's Law today. Hooke's Law has to do with the effects of springs on net force. So we all have used springs before, and we know that whether we compress a string or we stretch a string, it naturally wants to come back to its equilibrium position, back to its natural length. So as long as you haven't pulled it so far that it's now distorted, which sometimes happens, like think about like a slinky. How many times have you guys played with slinkies probably when you were kids and you pulled it too far and it distorted the slinky? So once that happens, it's not repairable, but as long as you're not applying too much force, they're always going to want to come back to their equilibrium position. So when a spring is being extended by adding its mass, the net force on that mass is going to be 0 once the spring reaches its equilibrium position. So if you have like this example with the fish on the scale, so some of you guys might be fishermen or so when you step on a scale or you weigh a fish, you're usually using a device that involves a spring. So whether you compress that spring like on a bathroom scale or you stretch a spring on like a spring scale, which is basically what this fish weighing scale is, the natural reaction force of the spring is to bring the spring back to its natural length, which we're going to call the equilibrium position. We know that each spring is going to be different, and we're going to talk about that. So here you can see this little GIF or GIF, however you say that, is showing this object that has applied mass to the spring, and you're just kind of like letting it drop and then letting it come back to its natural position. You can see on the graph here that it comes back to its equilibrium, or almost back to its equilibrium. If you were to let it continue, this graph would come back to its equilibrium. So at that point, the net force on the mass is going to be 0, because obviously the spring is applying a force, right? So the spring, in this case, it's trying to pull itself back to its natural position. So it's applying a spring force in the upward direction, and we know that the force of gravity is pulling this mass downward. So eventually it'll balance out and you will end up with an equal spring force to gravity force. So the effects of springs on a net force. We know that if we double the length of the spring, you're going to have twice as much force from that spring trying to bring it back to its equilibrium. So if I double the distance that I have pulled it out, so like from the second one to the third one, right? I've added twice as much mass. I'm stretching this out twice as far, and I'm going to have twice as much force in this last one than I would in the middle one of that spring trying to pull itself back to its natural state. Same idea would apply to if this were a sturdier spring and I was trying to compress it. So here we have some other examples. The little girl jumping on the trampoline. Trampolines are really good examples of this, right? So you have multiple different points of elasticity here. So the fabric that you're jumping on is elastic in itself. It has a little bit of give, not a whole lot. But then you obviously have springs all the way around it. So depending on the amount of force you apply will change the amount of force, the reactionary force being applied to you. So this cat is just trying to get out, but the little girl is light. She's not going to be getting very much reactionary force because she's not applying very much force to the springs to distort their position. Now, if we have something like this, a big jump is what I've been told this is called. So you have multiple kids, they're all applying force at the same time, but only the kid in the middle is absorbing the reactionary force, right? So he's just jumping like regular, and then as he keeps jumping, all of the other boys around him are adding mass to stretch out the springs. So when the reactionary force comes back and those springs come back to their equilibrium position, they're propelling just the mass of the buoy. So you're kind of tricking it, not really tricking it, but you're using these laws to your advantage, right? So you're applying 4 times the mass, so that reactionary force of these springs is being applied to one mass. So it's really getting them up there pretty high. So Hooke's law is what we're going to focus on today. And we're focusing on springs because that's like our typical example in physics for Hooke's law, but this also applies to other elastic materials. So this could be applied to anything like even like wood that might be moving around, elastic materials like bungee cords, other kinds of elastic bands like rubber bands, flexible materials like plastic and wood are also going to obey Hooke's law to some extent. So here with Hooke's law, what this is that the amount of restoring force, which is going to be F of S, like spring force, the restoring force of a spring is going to be determined by the extension or compression of the spring and its spring constant. Okay, so a spring constant is going to be a unique value to each spring. So as we talked about before, the material, the thickness or tightness of a spring affects how much it can be stretched or compressed. So the units K, which this lowercase k here, are going to be newtons per meter. Okay, so the unit for this is a capital N / lowercase m. What this unit is telling us is that the spring constant is the relationship between force and stretch or compression. The value of K is going to tell us how many newtons of force cause 1 meter of stretch. So therefore, the spring with a larger value for K, a larger spring constant, is going to require more force to cause a stretch or a compression. So this formula is what we're going to refer to. So we have F of S, so the force of the restoring force of the spring, whether that is going back to its normal position after being stretched or compressed. So the force of this spring is going to be equal to the spring constant, which this is a constant. This will be the same for any of the exact same springs. So if I had several springs of a certain size and shape, they would all have the same spring constant. And then delta X is going to be the change in distance. So if I am compressing a spring, that's going to be the change in distance in meters. So it's going to be pretty small values because we're not stretching springs whole meters usually. So you can either have a pull or a push here, but the distance that you have changed the length of the spring is delta X. So larger spring constants are going to require more force to cause a stretch or more compression. So normally, like if you think of examples of this, something that's very sturdy or very big is probably going to have a higher spring constant than something that is more of a loose coil, like a slinky. If you think of a slinky, they have a pretty low spring constant because you can very easily stretch them out and then they very easily go back to their original position. Okay, so if we try these out, just kind of getting some examples here. If you want to, I would recommend pausing the video for a second and trying to fill in the blanks here just to get some practice in using this formula. So we're going to use this formula up in the top right corner. So we have force is equal to spring constant times the change in length, which will be in meters. So if you want to do that, go ahead and pause it now. Okay, so if you aren't going to pause it and you just want to go through, we will do that. So for this first one here, to find the spring constant, if you rearrange this formula, you're going to want to pull you're going to get the K by itself, and then, hold on one second. All right, sorry about that. I had somebody pop in here for a second. Okay, so start from the beginning. So if we're going to use this formula in the top right corner to solve for all three of these values, okay, so we can solve for the spring constant. And if you are using the spring constant in a lab or a real life situation, once you calculate the spring constant for a certain spring, it's not going to change unless you've distorted the shape of the spring. So once you get that done, that part is kind of something you can use over and over as long as you're using that exact same spring. So the force applied will change based off of how much you're compressing or stretching the spring. And then the stretch or compression obviously will kind of circle back and be affected by how much force is applied. So if you're going to figure these out, the first one, we have a spring constant of 200 Newton meters. Force applied is going to be 200 newtons, so the stretch or compression. So we're going to have to divide these. So you're going to have the force divided by the spring constant. Okay, so in this case, 200 divided by 200 is just going to be 1. Let's see if I can't get, I don't have any of my pen tools on this slide for some reason. So we would plug in a 1 meter right here. So for the spring constant, you're going to rearrange this again. You'd end up with force divided by the compression of the spring. So here, make sure that force is in newtons, which it normally is going to be, but you might see it in pounds every once in a while. So make sure it's in newtons. Make sure the distance is in meters. That's something you'll have to pay attention to. So for the spring constant, we're going to have the force of 400 newtons divided by 1. So we're going to have just 400 Newton/meters for your spring constant here. On this next one, you're going back to figuring out the stretch or the compression. So the distance that this spring would have moved if it had a spring constant of 25 Newton meters and it had 100 newtons of force applied. So if we're finding the compression and the distance, it has changed. Again, you're going to have the force, which here we have 100 newtons, divided by the spring constant. So it's going to give you 100 divided by 25. It's going to give you 4 meters for your stretch or compression. And from these simple formulas, we don't know if it's stretching or compressing, but you will get that from the context of your question. So on the last two, we're trying to find the force being applied. So this one, we don't have to rearrange the formula at all. We're just going to have the spring constant multiplied with the distance that it has been moved. So if we have 700 times 0.5, we're going to end up with 350 newtons. So what that's telling us is 350 newtons is saying that if the spring constant is 700, we're going to have to apply 350 newtons of force in order to get that spring to move 0.5 meters. So on the very last one, we have 250 Newton meters for the spring constant. We're going to multiply that with 2 for the distance that it's changed to get 500 newtons down here. So we have 3 examples here. First one, we're going to find the length of the spring, that's how far it's been stretched. So a fish with a mass of 12.9 kilograms is attached to a Newton spring scale. So I don't know if you guys we've used these early in the year, but the spring scale, again, is what you're going to use today in the Gizmo. So that'll be kind of helpful to see this. So the spring scale is basically just a device used in physics. It has a spring inside with a hook on the end, and you're pulling it, and it tells you how much force has been applied. So we have a fish of a mass of 12.9 kilograms attached to a spring scale that has a spring constant of 665 Newton meters. Determine the stretch of the spring. So what do we know? So if we look on the left-hand side here, we have, let's see if I can get this. Ooh. Okay, so we have our free body diagram, and again, free body diagrams are required of these. So we have the circle representing the fish. We know the mass of the fish is 12.9. The first thing we want to do is get the basics out of the way. Okay, so we need to figure out what the force of gravity is on the fish. So if we know his mass is 12.9 kilograms, I have to stop moving this mouse so that little menu stays out of the way. So if you look just beneath this in the green writing, you have the force of gravity is equal to mass times our gravity, the acceleration of gravity. So we're going to have 12.9 times 9.8, and that gives us 126.42 newtons. So we know that the force of gravity acting on the fish is 126.42 newtons. We're trying to figure out the stretch of the spring once this mass has been applied. So we also know that we know the mass, we just use that. We know the spring constant for K is going to be 665 Newton meters. So the first step we want to look at is to figure out Fs. So since acceleration is 0, it's just we're going to assume that it stopped moving. We've applied the mass and it's just kind of hanging there now. We can also make the relationship that the force of the stretch is going to be equal to the force of gravity on that object. So if we know the force of gravity is 126.42 newtons, the force of the stretch had to also have been being applied is 126.42 newtons, which makes sense, right? Like the mass is what's the only force being applied to the spring, so the force being stretched out had to have been 126.42 newtons. So for the second part of this, to find the stretch of the spring, we're going to use our formula. So F of S is equal to K times delta X. So we have the force of the spring is going to be equal to the spring constant times the change in position. So here we're going to rearrange this formula to solve for the change in position, which is what we're trying to find, the length. And we are just going to sub that in. So just like we did on the table before this, you're going to have the force divided by the spring constant to give you your delta X. So once we divide that, we get 0.19 meters. You can report it in meters, that would be fine, but this would probably be more appropriate to report in centimeters just because of the scale of the size of this object. So the spring was stretched by 17 centimeters or 0.19 meters. So for this next one, we're going to be finding the force. So on the previous one, we were finding delta X because we already had the force being applied because we knew what the mass was, and then we had the spring constant given to us already. So on this second one, we're going to find the force required here. So a composite hockey stick with a spring constant of 9,481 Newton meters bends 5 centimeters during a slap shot. So how much force did the stick apply to the puck? Okay, so if you are you're swinging a hockey stick, in the process of hitting the puck, that stick bends 5 centimeters. So because it bends, we know that it's going to kind of snap back to its equilibrium position. So in that process, how much force did the stick apply to the puck? So what do we have? On the top left corner, we have the spring constant is 9,481 Newton meters. Just because of the fact that we have a very high spring constant, we know that the amount of force is going to be pretty high here. So we have the distance, which was given to us in centimeters, but we need to convert that to meters. So we're going to move our decimal point over, or you can divide it by 100. But if you have 5 centimeters, it's going to be equal to 0.05 meters, and we're trying to find the force that's going to be applied. So here we do not need to change our formula at all. We don't need to rearrange it. So we're finding the force of the spring. So we're going to have the spring constant, 9,481 times the distance in meters that the spring was moved. So 0.05 meters. So it's going to tell us that our force of the spring, the stick applied 470 newtons of force to the puck. The very last example here is going to be finding the spring constant, okay? So on this one, we have a 61.2 kilogram bungee jumper jumping from a bridge. She's tied to an 11.2 meter long bungee cord that's unstretched, right? So that'll matter here when we're figuring out how much it's stretched, and falls a total of 32.4 meters. Calculate the spring constant of the bungee cord. So when we think about spring constant, we know that we have our formula of F equals K times X, or F equals K times delta X. So we're going to have the spring constant times the distance that it has moved. So what we need to figure out, we need to figure out what the force is, and we need to figure out how much it has been stretched before we can figure out what the constant is. So this little diagram at the top left here, and this is going to help us figure out how much it actually stretched. So we know that the bungee cord is 11.2 meters long, unstretched. So that's just like laying flat or hanging straight down with no mass attached to it. But if the girl falls a total of 32.4 meters, we have to figure out what the difference is here to figure out how much we stretched that spring out. So if she jumped downwards, it's already 11.2 meters. The entire distance she jumped was, or the entire distance she moved was 32.4 meters. So we need to find the difference between these two to figure out right here. So we're going to find the distance between the unstretched amount of the bungee cord versus what she actually moved. So the distance this bungee cord was stretched was 21.2 meters. It's already in meters. We don't need to convert that at all. So we are now going to have to figure out the force of this person on that bungee cord. So we're going to figure out what her mass was. Okay, so we're going to figure out, or we know our mass, we're going to figure out our force of gravity. So the force of gravity is going to be her mass times the acceleration of gravity, which is 9.8. So we're going to get the force applied by the person on the bungee cord is 599.76 newtons. Now, we talked about this like on the second slide, I think, or the first slide, that when that comes back to equilibrium, the force of the spring and the force of gravity is going to be equal. So we're assuming that the bungee jumper has settled out, like she's not bouncing anymore. She jumped and now she's just kind of like hanging there, waiting to be pulled back up. So the force of her body is applying 599.76 newtons downward, which means that the force being applied to the spring is also 599.76 newtons, because it's equal but opposites. It's similar to normal force. So now we have the distance that the bungee cord has been stretched of 21.2 meters. And then we have the force S. So the force of the spring is going to be 599.76 newtons. We're going to substitute that into our formula here. This part's just kind of been reworded, but we know that M times G is going to be the force of gravity. So we already know that relationship. So we already figured that out down here. So we're going to substitute those values in. We're going to have the spring constant is equal to the mass, the force being applied by the mass divided by the distance that the spring was stretched. So in this case, we're going to have that the bungee cord has a spring constant of 28 Newton meters. So what this could be useful for now is if we know that this bungee cord has a spring constant of 28 Newton meters, you could then figure out how far the next jumper might go based off of their mass. So if this person is 61.2 kilograms and you're trying to figure out how far someone that is 90 kilograms might fall, that would be important, right? Depending on how far the surface is beneath your jump. So you could then use the spring constant of 28 Newton meters and then go back in and substitute in the new mass to figure out the distance that would be changed. So those are the three examples we have. The assignment for today is very short. It is, let me see, 2 questions. Nope, 3 questions. Okay, so it's 3 questions, and you have some summary questions to just kind of like circle back with the different types of forces that we've talked about. We are going to do Hooke's Law on a Gizmo, so I'm going to pause this for a second and bring you over to that section. So if you want to hang out and kind of see how Hooke's Law works on the Gizmo, just hang tight for a second. All right, so here we are on the Gizmo for determining a spring constant. So when you guys are on this one, let me see if I better not make it full scale. Okay, so what you have here, you're going to have a mass hanging from a spring, and then we're going to use different types of springs with different types of masses just to kind of get a visual representation of what's happening here with Hooke's Law. So this is a very, very basic concept. It just gives you a good idea of kind of what's going on here. So here first, to use this Gizmo, you're going to want to click on this little weight plate and hook it to the hook of the spring. You can see here that the distance changes, so you're going to have to pay attention to that. So like measure where it is first, so it's at 5, and then we add the plate and it settles out there, maybe like 5.6 or something. So right in there. And then you can start adding masses. So if I add this mass here, it's obviously going to stretch it out. You can add all the masses and change this up. So you can record data. Okay, so if you record your data, and it's going to give you some information over here. You can go to your graph, and it's going to show you what the stretch of the spring was. It's going to show you your spring constant and the force. You can also click on the table, and it's going to give you some very like specific information for like this set of data. So if I change this to the next spring, woo, that one is a little more stretchy. The third spring, they're all going to be a little bit different. Okay, so this is what it's asking you to do. The description is just giving you some information on like what it's doing, but you're basically going to work in the table and graph section of this. So when you guys open this up, find this here. Okay, so when you guys open this up, this is a shorter gizmo. It's only 3 pages worth of questions. So when you guys open this up, you can click on this. This is a link to the website. But it goes through very specifically like what all of these different vocabulary words are and kind of like giving you visual representations of it. So for this one, you guys are, I think, only doing, we're only going to do the spring force activity for this. So it's going to have you do a little bit of converting. You're going to find the mass of the scale. And then here is kind of where you're working from. So you're going to just compare the force versus the displacement for each of these different masses. And then there's a little bit of analysis to go along with that. So hopefully you guys can get through this today. I know I've been gone for the last 2 class periods, but for all you in-class kids. So please, if you're having any questions, feel free to stop by AC Lab, or I could probably stay after school for a little while on like Thursday or Friday. So we do have our test coming up. It's going to be next week. So next class will be spent just reviewing all of this unit. So if you do have questions, please get them to me sooner than later. Don't wait until you see me again next time, because then I'll be rushing trying to get things cleared up. So also just a reminder in case you didn't see it, number 6, I think I made an announcement about it, but number 6 on the friction homework is optional. It's going to be extra credit. So if you get it done correctly, you get your extra credit for it. But if not, it's not a big deal. So it uses angles being involved there, and we hadn't actually talked about that yet. So go ahead and get this done. Make sure that you let me know if you have any questions, and I will talk to you guys soon.